Good afternoon, everyone. Welcome. My name is Francesca Jacobi from the University of Technology, Sydney, and I'm also chair of currently of the New South Wales EDS, so Electron Devices Society chapter, local chapter, and I have the pleasure of giving a short introduction to this. I believe it's a fourth event that we organized this year in 2021. Most of them virtually, but hopefully next year we'll resume some of the in-person events as well. And actually, this is a joint. I will let my colleague Yang Yang to introduce our esteemed speaker today, and I just wanted to give a short introduction to the joint event. So, but first of all, I would like to acknowledge that we are here hosting this webinar from the lands of the Gadigal people of the Aurora Nation. And we also acknowledge the traditional custodians of the various lands on which you all are dialing in from today, and pay our respects to the elders, both past, present, and emerging. So again, it's with great pleasure that we have our speaker, Dr. Ranjith Unnithan from Melbourne. First of all, a brief, Yang, if you could just move to the next slide. I just wanted to say a couple of words about EDS. So the IEEE Electron Devices Society is promoting excellence in the field of electron devices for the benefit of humanity, and particularly the field of interest of EDS is all aspects of engineering, going from physics, theory, experiments, and such concerning electron and ion devices. And there's a long range of clear classes of materials that are concerned in all of this, up to from insulators, metal, plasmas, processing, and up to, of course, emerging materials. It is very important and timely topic. And if you can move to the next one, Yang. And yes, last but not least, I also wanted to say that today we are really glad to host this in collaboration with the ARC Center of Excellence in Transformative Meta-Optical Systems. And the Center of Excellence is a relatively new one, just been launched, well, not officially yet, actually, but just started about a year ago. And it is very relevant to the topic of our lecture today, because within TMOS, we actually focus on generating, manipulating, and detecting light in very flat, very miniaturized systems that are based on meta-optics and metamaterials. So without further ado, I would like to leave Yang Yang now to introduce our speaker today.
Thank you very much, Francesca, for the opening of the seminar. And good afternoon, everyone. Thank you for your time today attending this workshop that hosted jointly by the IEEE New South Wales EDS chapter and as well as ARC Center of Excellence TMOS. The invited speaker, Dr. Ranjith Unnithan, is from the University of Melbourne. Ranjith is a research group leader and a senior lecturer at the Department of Electrical and Electronic Engineering at the University of Melbourne. He is also the director of sensor research at the Hot Eye Pty Ltd. His research areas span novel multispectral imaging sensors, AR displays, sensor electronics for the biomedical applications, drone-based sensors and applications. Ranjith successfully completed his PhD in electrical engineering from the University of Cambridge in November 2011. Following the completion of the PhD, Ranjith worked as a postdoc researcher and project manager in the electrical engineering department at the University of Cambridge on a Samsung electronics project. He started his position of a scientist engineer at the Indian Space Research Organizations in Bangalore, and he was involved in the India's first mission to moon, Chandrayaan #1. He was awarded with the Young Scientist Award by His Excellency. Ranjith has a great passion for the innovations and the entrepreneurship. And Ranjith has won the Transband Innovation Competition in 2017, and he also has many awards and achievement over the last few years. So today's talk is related to one of his recent projects that funded by the RC Discovery Project. So let's welcome Ranjith to deliver the talk. So I will stop sharing, and so maybe Ranjith, you can share your slides.
Yeah, good afternoon. So Yang, maybe I will turn off my video once I talk the talk because of the bandwidth issues. So good afternoon. Firstly, I thank Dr. Yang and Francesca for the invitation to deliver this talk and their kind introduction. I also thank IEEE EDS chapter in New South Wales and ARC Center of Excellence TMOS for sponsoring this talk. I consider it as a privilege to come and talk to you. Today I will be presenting one of my major research directions, that is multispectral imaging using metasurfaces. So I have got other research directions such as augmented reality displays, sensor electronics, CMOS image sensor design. I'm mostly interested in translational research, so that I will be sharing some entrepreneurial tips today during my talk. It doesn't mean that I became a big entrepreneur, but yeah, at least I started doing some entrepreneurial activities, and I found out my hand burned, and so that your hand will not be burning if you are going in that direction. Well, I learned from failures, because we started 5 and only 2 proceeded. So it is like amplifier design. If you design an amplifier and if you learned, the signal is amplifying. So you put everything together on the breadboard, so you learn nothing. But if your amplifier is not working, you will learn a lot about bandwidth, noise issues. The same way, I have been learning a lot from this entrepreneurial activity. Some tips I can share with you. So also I will try to keep my talk less technical, means I'm not going to use any big equations or technical complexity to put you to a deep sleep, especially these days if people sleep over Zoom talk. Today I will be presenting maybe 1 or 2 key research work. We published so many papers, and we have patent, we have trade secret, we have several IPs. So I will be presenting maybe 1 or 2 key research work that was carried out in my research group since 2014, since I started my group at Melbourne. So this work was actually pivotal in our startup formation, and I will also give you some tips, as I mentioned, based on my experience. To catch up with the bandwidth, maybe I will turn off my video. Otherwise, sometimes there will be some delay when the presentation comes.
Hi, Ranjith. Yep. Would you mind please share your screen?
Yes, I'm going to share my screen, but just let me some technical issue. Because I can't share anything. Yep, I think no, yeah, I can't share. Sorry, it was fine, but due to some reason,
okay, yeah. Let me just double check this setting here.
Because when we checked it was fine, but I think after that, something happened.
Yeah, I think you are the co-host. You should be able to share. Do you want to try again?
No, I think it's. So what I can do is I can just leave and join again, maybe. If that is fine.
Yep.
Yeah, it doesn't allow me to share actually. Yeah, so what I'll do is I'll just leave and join again. Sorry for the inconvenience.
Strange. It worked very easily before.
Ranjith, can you hear us?
Yeah, I can hear you. So I'm joining from another platform.
Oh, okay, that's right.
Okay, so
Because
that will be.
yeah, because your screen is like a black. Sorry,
Yeah.
a red color, but can't see anything.
Yeah, sorry for the inconvenience. I don't know what happened actually. Yeah, when we checked it was fine, but something, went wrong actually.
Yeah, no worries.
It's very strange. So Ranjith is co-host, right? So it's...
Yeah, Ranjith, I made you as a host now. Can you try?
Yep. Yeah, thanks, Yang. I think it should be fine now. Yeah, I think I can log in.
Yeah, no worries.
You should be in now.
Yeah, so I'm going to share the screen now.
Yes, it works.
Yep, open now. Can you see the slides? Yep.
Yep, we can. Yep.
Yeah, thank you very much. And sorry for the inconvenience created because of the connection issue. Yeah, so multispectral imaging using Metasurfaces. So this is the outline of my talk. Introduction, then multispectral imaging in the visible and near infrared. So then I'll be talking about our first startup, Hotai Private Limited. Then Metasurfaces as color filters or color mosaic. So that led to another startup, that is Big Sensor Private Limited. Then we also work on the multispectral imaging and machine learning, that is in the thermal domain, thermal wavelengths. Yeah, then I will conclude. So everybody knows the history of the color camera. So the first color camera that was invented many years ago. So we can't say a date because in different countries, this concept was originated in different level. So this is one of the color cameras where you can see in the first camera, they have used 3 sensors. So one for red, one for green, one for blue. So these are the primary colors. By mixing these 3 primary colors, you can make millions of other colors, but you can't create the primary colors. So we use this RGB, red, green, blue, to create rest of the colors. So that's the reason they have used 3 sensors. And then later people found out using these 3 sensors create a lot of inconvenience. The system is, you can see on the left side, is bulky. You need a lot of processing electronics. And then that led to inventing a filter mosaic by an engineer in Kodak. And these days you can see a lot of digital cameras, as you see here. So these are the digital cameras in the market. You can also see the smallest size camera made by OmniVision. So pixel structure. So maybe before I go into my talk, maybe it is a good idea to give an overview of the pixel structure. So if you look at the CMOS image sensor, maybe you can take it to a lab and see under optical microscope. Then you can see this mosaic, red, green, blue. And if you take a cross section of 1 pixel, then you can see a micro lens actually on the top of each pixel. Then you have got color pixel, red, green, blue. So that's the reason you see the color. And then you have got the photo detectors, and then you have got all the electronics. So this is a back illuminated structure. So in the image sensor, you can see bare mosaic. In the bare mosaic means you see more number of greens than red and blue. So bare mosaic is widely used as a color filter array because our eye is more sensitive to green. So bare basically mimicked the same on the image sensor. Bryce Baer, again from Kodak. So they developed this bare pattern. So once we have bare pattern, then our images will be more sharp, and then we can get, pretty much similar to our human eye, because that's what our standard is, human eye. So making a camera that is closer to the human eye is the best camera. That's what people are trying to do. So everybody knows how the color camera works. So we got red, green, blue filters. And then how these filters work is they absorb a particular band of colors and transmit only the selected color. You can see here. And then you will be getting missing. So if you take blue alone, then green and red are missing. If you take green, then blue and red are missing, and hence, blue and green from the red. So then the missing information, they use a interpolation technique, and then they can get red, green, blue colors, and what they do is they combine, and then you get a color image. Excuse me. So this color filter in the conventional image sensor, the thickness is in excuse me, in micron size. So if you don't have micron thickness, what will happen is you don't get enough absorption, so you don't get the color purity. And then this one got 3 bands, so then you can get 3 colors. But then this one you can't use for multispectral imaging. So why? Because in the multispectral you need narrow bands. So in the conventional color filter, the problem is, you can see the spectral width. So this is wavelength versus transmission. So the spectral width is maybe around 80 to 90 nanometers width. So there is an overlap of the spectral features. So you cannot use it for multispectral imaging. So I will introduce multispectral imaging in the coming slides. So these are some of the other pixel geometry. So we also work on the CMOS chip itself. So we have got 2 research directions in my group. One is on the color filters and color filter mosaic. Another one is on the chip design. So that one I will not be presenting today. I will be presenting the multispectral work. So why we are doing this chip design is our interest is how can we make submicron pixels? Because these are the front illuminated CMOS architecture. You got the micro lens, color filter, then you got the metallic, the electronics. So these are the front illuminated. So back illuminated means when you have pixel size around 1.1 micron, then it is very difficult to have a tunnel like here so that the light will not come here in the front illuminated. So it's difficult. So that's the reason they developed a back illuminated. But then why we are interested in submicron pixel is it is not a scaling down problem, because from 1.75 micrometer, you can come to 1.1 micron. But when you come to say 500 nanometer or 400 nanometer, the first problem is your color filter. You can't put a pigment-based or dye-based color filter, because then it will be very thick. Your pixel size is in the nanoscale, but then the thickness is in micron scale. So the coupling will not be good. And then the lens also, you will have trouble when it is coming to the submicron scale. Then we also want to study the noise. So that's the reason we designed actually a chip and we fabricated in ST microelectronics. At the moment we are testing. So our pixel size, we got two designs. One is around 1 micron and another one is around 500 nanometer. So Samsung already developed a 0.7 micron in 2020. And also Sony and Samsung, so they are the companies at the moment who got submicron pixels. So Sony got a 0.8 micron, Samsung got around 0.7 micron. So we got in our chip, this is our chip, we got half this much area less than 1 micron. So that is using conventional design. Then here, what we are doing is we are using a new type of light sensitive transistors to reduce the pixel size to 500 nanometer. So as I mentioned, just this part, I will be leaving this part and going to my talk, but I thought I will highlight this part because at the moment in the image sensor, the size, pixel size is not because of the detector. Photo detector you can make in nanoscale. The trouble is with the transistors. So you need around 3 transistors around the pixel, as you see on the right. So we fabricated using 28 nanometer semiconductor process technology. So 28 nanometer is not the size of the transistor, but it is between the width of the channel, the length between drain and source. But in 28 nanometer technology, the size of the transistor is still 150 by 120. So that is the problem in designing, scaling down the pixel size to submicron. So in our normal design, we are using transistor itself as a light detector. And then that is our new design. Okay, so my talk today is maybe that talk I can give another time. So today I will be discussing about a multispectral camera. So what is a multispectral camera? So multispectral camera captures image data within specific wavelength ranges in a narrow band. So that's what I said, this spectral width is narrow. If it is overlapping, you can't extract a lot of information actually. So this width again, depending upon your application. In some application in the precision agriculture, you need around maybe 3 nanometers. In some application, again in precision agriculture, you can have 20 nanometers. So depending upon the application, you can find out the required bandwidth. So the application, there are so many applications in this multispectral imaging. So it was originally developed by US Army for detecting objects in different terrains. Later, people started adopting the technology to different fields like healthcare for monitoring the skin, and even in the surgery, they use multispectral big cameras, aerospace, in the military, forensic mining for classifying the minerals, and in remote sensing. So we got first interested in remote sensing. So you can see in the conventional multispectral camera, people use multiple sensors and electronics. So you can see these are the 4 cameras, and then they use 4 filters, and then you have got 4 optics. So that is the camera optics. So that's a conventional multispectral camera. So it's got a lot of applications, as I mentioned, in remote sensing, agriculture, archaeology, medicine. So there is a big market actually for multispectral. You can see the trend in general, the spectral imaging. So then it is difficult to explain the concept of multispectral because whenever I gave a talk, so people ask, exactly how this multispectral help us getting the information, which we can prove using some algorithm. But then I want, people to be visualizing. So this is one couple of slides I prepared so that I can explain properly. So I have used a Cyto Viva hyperspectral spectrometer. Then I have taken a healthy leaf, yellow leaf, and a dead leaf. You can see. So if you take the spectrum, you can see the spectrum. The spectra are different for these leaves because of the healthy. You can see some dip around 700. For yellow, you can see some reddish, and then this one is some the other one. So then, if you image this one with a broad spectral width like a normal camera, you won't be able to distinguish actually. Yeah, well, because this one got, almost at the end of the life, this dead leaf and this yellow leaf, this healthy leaf. Using a normal camera, this one you can now distinguish. But actually, if there is a slight variation, then these spectral differences will be very, very small. So that if you image with RGB camera, what will happen is you won't be able to find out the difference. So then for that, in order to find out the difference, what happens is you have to image in a narrow band. So when you are using a multispectral, say 3 bands, if you are using a 3 bands, then you can see this only this much region. And then you can see that if your camera is not in the right position, you will not get the required information actually. So you also should know the problem before finding the solution. Suppose in the remote sensing, sometimes people can do blind remote sensing because their sensor might not be matching with what they are looking for. That is because they haven't been investigated correctly the problem. So that's, as I mentioned, if you want to find out this issue, and if your multispectral 3-band is working here, you don't get the information. But if you align it around 700 or even slightly before 700, you can capture it in a narrow range so that only camera is recording only this much information, so that we can get this information. So you can look at it. So this one is I have taken this image using a monochrome camera that can give the raw data, and then you can put around 710 bandpass filter, so you can see the contrast difference. So then this one, when there is only a small difference, multispectral camera can detect that one. So that is the whole purpose. So what we will do is we can define function like NDVI. So that is basically what it does is you can see it takes the ratio between. So this NDVI is differential, non-differential vegetation index. So what it does is it measures the reflection coefficient between NIR and RED. So we will be making something coefficient, some function. We will define some function similar to NDVI, and then we can find out actually the plant health. So then what is the advantage of multispectral in the plant health? The advantage is if you go to hectares of area, say apple plantation or vineyard or any other kind of plantation, there is no point in getting the getting the imaging done, and then you find out, oh, it's gone. Then why you should spend money again for the imaging? Maybe that images only will be useful for the getting some insurance back. So this multispectral, the advantage is you can pick up this plant health using this technique before it appears on the leaf, or before it is visible to human eye, or before it can be captured using a normal camera, so that farmers get an opportunity to fix the problem. It could be due to over watering, or under watering, or over fertilizing, under fertilizing, whatever the thing. So we can find out. So these are some of the examples of the multispectral imaging in the remote sensing. So you can see in the precision agriculture, you can connect this multispectral to a drone, and then the drone will be taking so many images, and then we can stitch together those images using the GPS location. And then you can find out the plant health, like, this is a dead leaf, this is a stressed leaf, healthy leaf. Yeah, I'm using only NDVI to show you the concept, but we will be using a powerful algorithms and running those algorithms. So it will look something like this, so that you can see the reddish is high stress. So this is in the hectares of area. And then you can also monitor the soil. And yeah, in general, we can predict the plant health. Then you will ask, can we spot a particular disease? At the moment, none of the precision agriculture startups could sense a particular disease actually. You can maybe broadly classify this comes under this disease. Yeah, which will be more than sufficient so that you can fix the problem. So these are some of the cameras existing in the market, so that they are using the discrete sensors like Tetracam, Centira, and MicaSense, and they cost from US dollar 10K, so it's like 15K to maybe 25K Australian dollars for 6 bands. Then the problem with this camera is obviously it's expensive, and no custom-made bands, or the limited bands, not tailored for an application. It's like if you buy this camera, the problem will be, if you don't know the problem, this camera will not give you some, a lot of information. It will give you some information. It will be like doing blind remote sensing, not an informed remote sensing. So that is a problem. So then we encountered this issue because we were doing some research on the precision agriculture. So that led to our first startup called Hot Eye Private Limited. So we decided to make our own sensors for this multispectral imaging, especially for the precision agriculture. So then we had a clear definition. So a purpose-driven research with a clear understanding of the problem will lead to new ventures. So that's the reason our Hot Eye Private Limited was successful. And we also got investment. That is the main reason our first startup became successful. So entrepreneurial activities can be successfully started through interdisciplinary collaboration. So I'm not underestimating the power of interdisciplinary collaborations, because people often talk interdisciplinary collaboration, but definitely you can do a lot of research which is otherwise not possible using ideas from or integrating ideas from other disciplines through interdisciplinary collaboration. So this research started when I discussed with another colleague of mine, Dongriel, associate professor, about sensors, because my expertise is on sensors, sensor electronics, and then he was talking about the issues in the precision agriculture, which led to this Hot Eye Private Limited. So it's an interdisciplinary initiative between electrical infrastructure, remote sensing. Then we also collaborated with a drone company, because it is difficult to fly a drone by ourselves because of the license, insurance, because these cameras you are fitting in, and if it is breaking, then it's difficult to recover the money. And also you should have a pilot license to fly the drone because of the CASA regulations. So that's the reason we collaborated with the drone company to start this company. So this is called a Hot Eye Private Limited. So you can see, so this is a startup from the University of Melbourne by team members from different departments like electrical, infrastructure, and we partnered with XM2. So that's a drone company. So you might not know XM2, but you might have seen what XM2 produced, because XM2 provides service to Hollywood. So the Pirates of Caribbean and all the movies, the aerial images were actually provided by XM2. So they have got excellent drones and video cameras. So what we provide is, we provide growers actionable crop analytics and insights to help them make timely and best decision of resources like water, fertilizers, and pesticides. So as I mentioned, the early intervention, so that's what we are attempting, because otherwise finding the solution is not going to help farmers. So then people will ask, what is the innovation in the camera design? So the innovation, so we made a low-cost, custom-designed multispectral camera. So innovation is in the sensor design, the architecture. So that sensor design also can be an IP. So if we can make it with the new features and with low cost. Then we also got innovation in the sensor-specific algorithms, because some of the algorithms, the problem is that is not tailored for a particular sensor. So when you are putting in values, you might not get very good results. So our another innovation in this company is sensor-specific algorithms. So these are the two IPs in the company: sensor design, architecture, and sensor-specific algorithms. So that's the reason I will not be talking anything inside the sensor for this one, because of the IP-related issues. So this is how it will look like when we put our sensor on the drone, and then you can take so many images. So this is a nice image, then we can process. So we will be collecting. So when you put it on the drone, we will be capturing images, maybe one second, 1 frame per second. So that when it is moving, so there will be an overlap of 50%. So we will be end up collecting maybe thousands of images. So that's the reason we will be recording the GPS information. So that using GPS information, we will be stitching all these images together. Then we will be processing. And so these are some of the examples for your information. So this is our first core sensor we developed that has 6 bands, very compact size. So then we also connected thermal camera, because the thermal can pick up heat information. That is a valuable information if you want to measure the water stress. Then we also developed one with wireless interface and 6 bands GPS, because wireless interface is required when drone is flying. You can't bring the drone down for modifying anything. And then we also developed another one that is our recent one, that is a global shutter. So the image sensor got a global shutter. So when you buy image sensor, there will be rolling shutter and global shutter. So rolling shutter means it will be averaging the pixels in a line by line. So that's the reason if you move your hand, you get a blur. Global shutter means it will read all the information in the pixel at once, so that it is prone to vibration. So I think these days you mostly buy global shutter. So this is an example when it is imaging from the 100 meters actually. So that our camera, even the course camera also gave excellent images compared to commercially available one. So you can see here, this one looks white because in the healthy leaf will be looking very bright in the NIR. You can see here. So exactly what is presented in the publications that we could reproduce actually from our cameras. And this is some examples of a park we imaged and stitched together. And then just for your information. So then you can also see we can take out different bands like RBB, GBB, RGB composition. So we can get, I think, a lot of information actually. Yeah, then the question is, so this startup actually led to a lot of questions, because from our own experience, we found out that the 6 bands, even though our sensor design is cheap, low cost, but the 6 band is not good when you have different sensors. For example, here you need, though it's a compact design, there will be an image co-registration problem. So image co-registration problem is because these optics that's looking at different directions, the images never will match, especially it is on a moving platform. Then again, it is compact and it's heavy for drone-based application, even though it is very small. So that made us to think maybe back in 2015-16, can we make a small multispectral image sensor that is only one sensor, but we should have multiple bands and kind of a coincide. So that is again, we got it from our own, how the problem that we faced. So then we thought of, conducting research in this direction. So that's the reason then we explored Metasurfaces, because then what we found out is if we can make some novel filter mosaic, then we can make our own image sensor multispectral. But then, pigments and dyes, again, it will not give you narrow band. Then we also started looking at metasurfaces. And before going to metasurfaces, people they are not in the field. Metasurfaces means that is artificial surfaces, and we can create new features like using the refractive indices of metal dielectric combinations that you can't otherwise get in the nature. These are the engineered surfaces. So you can manipulate light, either amplitude, phase, or polarization using metasurfaces. So the first one is a conventional metasurfaces demonstration. So you have got light coming, then this is a vacuum, then this is some conventional material, maybe a glass, so that it will be refracting. So if you got a negative index, it will be coming in this direction. So this is for maybe scientists. For normal layman, this is the demonstration. You take a glass of water, put a straw, so then you will see kind of there is a small shift. And if you got a metasurface, then or metamaterial, then what will happen is you can make a negative index. So it will look something like this way bended. Actually, this was demonstrated in another research group. So this is an example of a metasurface. So they have got a metallic ring, and then this will bend the light in the opposite way, means this way. So just like creating a negative index. So we also explored metasurfaces for making color filters. The advantages are we can get very nanoscale thick surfaces we can use for getting the colors. And the second one is easy integration, because we need only thin film deposition. Then we also got excited, we can make structures using EBL, but I can tell you EBL based technologies will not succeed at the moment in the market because you can't reproduce exactly. So we made first mistake was we relied on EBL based technology. Structures we made with electron beam lithography. So when we said to people, they also got excited. Yeah, that's a very good But then when we tried to mass produce, we failed actually. So I can tell you none of the EBL based work will go to market until it is like a top defense work. You need only like maybe 3-4 numbers, something like that, because the reproducibility is very low for EBL based recipes. So yeah, whatever the technology that you are making in the photonics domain, people might not invest if we say EBL, but they might invest if we say it can be produced using photolithography, because people know that photolithography can produce a lot of structures, because in the chip fabrication people are using photolithography. So then we thought, okay, we will look at the Plasmonics, and everybody knows what is Plasmonics. So these are the rapid, plasmons. In order to understand Plasmonics, you should know what is plasmons. So plasmons are the rapid oscillations of electron density in a metal when you excite with the light. So you take a metal and then you shine some light, you can excite some plasmons, you might think, but it's not possible because there is a momentum mismatch. So if you match the momentum correctly, you can excite some free electrons. So free electrons will be oscillating, and this oscillation, the coupled oscillation, actually that is called plasmons. So that will be propagating, the energy will be propagating in the interface of metal and dielectric. So I think the plasmonics is actually not a new area. So it is very interesting. When we did plasmonics, when we look at the St. Chapel or Lycurgus cup, you might know, people used actually plasmonics to get colors. So they did plasmonics without understanding the theory. So they could embed metallic nanoparticles in the glass, and they have got excellent colors, mass producible. Today, I can tell you, with all the nanotechnology, it is difficult to make something like this. What they produced, it's amazing, how they did these structures actually during that time. With the repetition is reproducible. Yeah, maybe that's a reproducibility is very important actually when you make something commercially viable. So there are two types of surface plasmons. Everybody knows it is like putting a stone in the water so that the water waves are moving. So same way, that is a surface plasmons in the metal surface. So another one is a localized surface plasmons. From the name itself, that is localized. It means it is located somewhere. So the localized surface plasmons you can get when you excite your light on the nanoparticles. So that's how in the stained glass you get the colors. So some of these were our inspiration, and we did we made color filters. So I also would like to acknowledge some of the international work happened during that time from Harry Atwater from Caltech. So he made a nano color using aluminum, and then integrated on the CMOS chip, and then they made a camera RGB, but within a broad spectral width. So same time, we also conducted research on the color filters, but the thing is, my focus was on the multispectral, but then this focus was on the making a new color filter technology. So they have made these color filters on a 150 nanometer aluminum film, and then they made holes and they varied the holes. And the spectral width between 90 nanometer and 180. So Ken Cross here, Ken is here, Deputy Director of TMOS, also conducted research, which shows Ken is always at the forefront. So Ken used nanowires as color filters, and then Ken also demonstrated imaging, using the nanowire color filters. So Ken's group integrated on the CMOS chip, and he also made detectors using nanowire-based color filters. So these are some of the examples from Harry's paper. And so you can see the raw image, and then they did demosaicing, and then white balancing, linear matrix, and then gamma correction. So when I saw this one, I got very tired. I told her, my goodness, it's not that easy to get the color. You have to get color correction, gamma correction. So I was a bit skeptical about our technology, actually, whether it will work because of this much processing. Actually, this much processing is involved in your camera, actually. Camera got a lot of processing involved to see the right color. Then, Dragomir, I think Dragomir is here. And in collaboration with Dragomir, actually, we did some work back in 2013-14 time. Then we also, as I mentioned, my interest was in multispectral, but then I decided to investigate some of the fundamental aspects, because when you are making whole array, how many holes are required to get a color? So we found out if you arrange three holes in a triangular manner, we can get a color. So you can see here from 230 nanometer, we could see the color. Then we also investigated if you are using this for the display applications, what are the challenges? Because we use a hexagonal arrangement for maximum transmission. But then when you use a hexagonal arrangement, the problem is if you are making a display, you will have stitching problems, see, because you got the gap here. So that you can see even in the submicron level, that's the problem. So your pixel will not be having a good shape. So if you display some image, then you got some issues. So we came up with some filling schemes, and yeah, we did this measurement actually at ANU. And when Alex was there, I was there, and yeah, which also shows, your team was also is at the forefront, and under the leadership of Dragomir. Then we came back, and then then we that was that gave us a lot of confidence when we did some filter work. And as I mentioned, fear of failure kills all the entrepreneurial skills. So when I saw the Harris paper and a lot of processing involved, means you can't make a realistic device working in the field, because if you need to calibrate each time and you have to do a lot of processing to get the required colors, then it is a challenge actually. So that, but then we decided, okay, anyway, we will try our multispectral, we will carry on, because our aim was how to reduce the spectral width and get the colors. So the previous demonstration, the spectral width was not a serious concern. So what we did is we took out a Canon 1000D camera and opened the camera. As electronics person, we are not afraid of electronics. And then we took out the image sensor using laser cutter. We removed all the protective glass. Then you can see the complication here. So then what we did is we took a chopstick and removed all the color filters from the Canon 3D. You can see these are the removed part. Then we also used some plasma cleaning, and so we could remove it properly. So you can see the scratched area. So this is the photo detectors, this is RGB filters, and these are the micro lenses on the top, like this cross section. Then what we did is we also took a CM, because nobody will give any of the information regarding the camera sensors, so that's so protective. And then we understood the size, and then we also did the profilometry, optical profilometry, and found out the thickness. And then my intention was to put a plasmonic filter. So you can see a plasmonic filter and then put it on the sensor and see whether we can see the color using the processing on the camera without any calibration. We correctly aligned using a flip chip bonder during that time. And then we found out, surprisingly, we got some color even without doing anything. So good thing was, we could put everything back in one piece, because it's a bit complicated to put everything back, after alignment. And then with this gave us some, good confidence actually. We can get some colors, without a lot of processing. So by the way, then we also saw IMEC, that's a big company. They came up with a single sensor based multispectral. So they are also doing the same work. So they released actually their camera sensor, but it's very expensive. So their technology is not using Metasurfaces. They are using a dielectric, mirrors, Bragg mirrors. So you can see different heights. So each pixel, they have got filters, but then it's got, maybe 20 or 30 layers each pixel. So the height is different, because the number of layers will give you different color filtering effect. So then this technology we saw. So IMEC. Then later, spectral devices, another company also is making single sensor based multispectral camera. So another tip is, if there are no competitors for your product, whatever you are developing, either you are at the forefront or your product has no real use. So that's what, what we have noted. If you don't have any competitors, either you are at the forefront or your product has no real use actually. So this is some of the research work we did. So in developing the single sensor based multispectral camera, the Metasurface, whatever we have developed, we did a lot of fundamental research as well. Because without that, we couldn't conclude it to one geometry. So I will be presenting, some of the fundamental researches here. So this is a multispectral sensor. So this is a color mosaic actually. So using Plasmonics layer only, you get a wide spectral width. So we put a dielectric metal again below so that we can make it narrow. So then we have made a RGB actually. So it's a fabrication is a bit complicated. Then we integrated on the CMOS chip. We removed the protective glass and then we integrated on the chip, and then we got actually a multispectral camera working. So this is a you can see we also got the raw image, and from the raw image actually we recovered the colors, and this is the Macbeth chart. So that's what the people use for the calibration. Then we also got RG combination, GB combination, and RB combinations you can see here. So then we also plotted on the CI chart. So this is based on our eye, how eye is sensing the colors. So that's became an international standard called CI chart, and where we plotted and we checked it, and it was fine. We also fitted on the drone, and then we checked whether it is working in the field, because most of the equipment work in the lab. When they take it out, when we take it out, it might not work in the field. So then we tested, the vibration and then the color sensitivity, and whether we are getting the required contrast. Then we also defined some function, and then we checked it, so that you can see on the left side we got some grass that is a dry and healthy combination. But then we took using the multispectral, using our small compact sensor, and we could actually find out from this color where are the dense green grass that is in the red color, and then compared to dry grass. So we defined something like not NDVI. So this is called a new vegetation index we defined. So the RB vegetation index. So you can define your function for your application actually. Then we also did some CMY color filters. So the CMY color filter, so that is different from the RGB, because it can give a lot of brightness. So that's the reason we also did the CMY color filter. So here also, why we did the CMY is in the CMY, even still now, we don't have a technology that is usable for submicron pixels. Again, if you are making submicron pixels, as I mentioned, we have a research program. So if you make submicron pixels, you can't have micron thick color filters on the top. So then in the CMY, that is lacking. So that's the reason we developed CMY filters with aluminum TiO2 aluminum nano rods. So we made a mosaic. You can see the spectral features. It's got a very good transmission actually, around 80%. And then we integrated on the sensor. And we removed the protective glass, and then we got a CMY camera actually. And then so these are the transmission. You can see the University of Melbourne logo. The transmission was very good actually. And some of the fabrication. So the fabrication is actually a bit complicated. And so our research on a single sensor-based multispectral started in 2014, and since then developed different topologies. But what we found out is just these Plasmonics filters, they are very lossy in the visible region. You can't get more than 20-25% transmission. So we published the results not commercially viable. But our 6 years of research led to some filter mosaic technology using a new Metasurfaces, that is a metal dielectric based, a new design. And that can be mass produced. As I mentioned, the Plasmonic one also we got trouble. Some of them are good, but then we can't mass produce those. Each time when we make it, there will be some shift. And so that became a trade secret actually, our new Metasurface design. But we found out the Plasmonic filters, some of them are useful in thermal wavelengths. So then we also started in the thermal wavelength region. So we also work on the thermal wavelength region. Multispectral. So this is one of the commercial multispectral thermal camera. So this got 6 bands, but will cost you 1 million, and you have got a waiting time of 1 year. And so we also developed a multispectral with machine learning. So in the machine learning, we have made this is not a single sensor based one, but it's a compact, maybe slightly, maybe 2 credit card size. And we will be training with simulated data, and then we can recover actually full spectrum from the 6 bands, so that it got a spatial information, and this can recover the spectral information. So we also did some work on the single sensor based thermal work, and that is still ongoing work. So if you're interested in the machine learning, though, this is a machine learning technique that we developed. We developed our own machine learning technique because the MATLAB one got a lot of limitations. So this one is a convolutional neural network based machine learning technique. So this is our second startup company that is called PIC Sensor, where we will be making sensors for mainly agriculture applications, single sensor based one. So this is a filter technology we developed that can be mass produced, and so that's the trade secret actually at the moment, and IP for the PIC sensor. So these are some of the images you can see from the 6 bands, and so this is a colorful image on the top that is from RGB. So then you can take out each band images. Yeah, so I think I will conclude my talk here, maybe because of the time. And so publication-driven research produces good publications. So definitely publication-driven research, is very important. But then if you are looking for a particular application, you also have to do a translational research. So we find the, okay, this will solve the problem. But then from that, we have to do a lot of research actually in order to make a prototype working, or something that can be commercially produced. If the research is identifying knowledge gaps, the research innovation is trying to sensibly fill the gaps. Because most of the time when I work with the people, so they are, a little bit scared about the innovation part. They think that, many things can go wrong. But actually, by doing that one, you are also sensibly filling the gaps as well, not leaving the gap, or not just measuring the gap. What is the knowledge gap? Then we optimize it, but not, sensibly filling. So actually, the innovation is actually sensibly filling. Then blue sky research will lead to deep space. Definitely, blue sky research is important. But if you are interested in entrepreneurship, you have to land on the ground, because sometimes many people, they stay only on the blue sky and maybe go into the deep space, which is, people's different passions. So my definition of entrepreneurship is finding a useful solution actually to a problem, and with a benefit. There should be a benefit, but not always be making money. So because young entrepreneurs, they think that entrepreneurship is always making money, but that is not correct. So academics are in a unique position to start companies, because they have a platform to stand on, because they don't need to pay their bills. They don't need money, because it might take time to catch up to your company, so that you have money to pay your bills. So that's one big problem when people are starting a company when they are not working. Then some skills like confidence, patience, honesty, emotional intelligence, and interpersonal skills are essential for entrepreneurship, but there are exceptions. So as I mentioned, I was involved in 5 startups, but only 2 went ahead because of various reasons. Happy to discuss. So these are, if you want to know more about our work, there is a book we are publishing in Springer Nature in 2022, Jan, multispectral imaging using multispectral image sensors using Metasurfaces. And then our work also was on the cover art. And then we also work closely with Australian Defence, and this is a magazine in the connections about our work. So these are our main funders, Australian Research Council and Australian Defence, DSTG, DSI, then HOTI, KDH Design, Taiwan, Digital Falcon. Then we fabricate a device at MCN, and then we also use NCI facilities. Maybe I'll stop here, and thank you. Any questions?
Thank you so much for this wonderful talk, Ranjith, and it's very impressive. I think we have a question in the chat window. So,
I will check.
Yep, please have a look. And I think the question is about the application scenarios for different level of the grant.
So I think the first question, let me check, I think. For effective anomaly detection at the multi-level, varying altitude or specific aspects that you would consider selecting both optics and algorithm perspective. For example, low ground level versus ground level versus satellite monitoring. Yes, that's a good question. Yes. So if it is a satellite based, because the problem with the satellite based imaging is when you have clouds, you miss the data. So that's the reason farmers then they can't get reliable data when they want it. For example, they want to monitor because the crop getting ripe at different timings. Even though there is a season, but the timings might be different for you depending upon your crop, particular type of the variety that you are using. So when you want it, you don't get maybe the satellite-based data. So that's the reason people are looking for the drone-based solution so that they can immediately fly and get the data. Definitely, yes, it is depending upon the optics. If it is, the optics will be heavy. Actually, heavy optics are required if you are imaging from the satellite. And for the drone one, you are imaging around 100 meters.
Thanks, Ranjith. I see that Landfu from ANU has a question. Land, do you want to ask?
Yeah, thank you. Thank you very much, Ranjith, for a very, very nice talk. My question is that what you mentioned that when no matter whether you use a dye or you use Metasurface as a filter, you will always have some optical loss there, and which might just resulting the less sort of response of your detector. So my question is that what is the performance, the practical performance parameters that will make, the application really viable? For instance, if you put your camera onto a drone, what kind of responsivity or detectivity after having this multispectral sort of filters will be really needed for practical application?
Yes, so good question, Landfu. So as I mentioned, the Plasmonics, if you are using just the Plasmonics, that is very lossy. Even if you use gold is less lossy in the field, the wavelength range we are interested. So yeah, practically when you are making, you might end up having like around 22%, but you can make your camera working in the field around maybe 35%, 30-35, you can make it working because you can increase the gain of the camera. But then you can't increase the gain of the camera too much because then that also will increase the noise. Then what we have done, is because we are integrating this filter, then we buy a very high resolution image sensor, and instead of covering 1 pixel with one filter, we might be covering maybe 4 pixels with one filter. So that because that's a monochrome, so that it will be getting more light in for a particular band, and then we increase the gain slightly. So that's what we are doing.
I just have one more question about how big is actually your how many pixels do you have actually for your testing on the camera, and how big is the total sort of area?
Yeah, so the image sensor that we are using in, so we made 6 bands, then we made 4 bands. So the image sensor we used is around 20 megapixels in around 1 centimeter by 0.7 centimeters, something like that. So that's the image sensor we have used with global shutter.
Thank you very much.
And thanks, Ranjith. I see there is another question from Daniel.
Yeah, please.
Yeah. Yes, this is Daniel. Can you hear me okay?
Yeah, I can hear you. Thank you.
Great. Doctor, I was a little concerned. The startup company is trying to protect its technology with trade secret. But just like you were able to determine the parameters of the Canon camera by just taking it apart and then scratching away at the surface, couldn't some competitor wannabe try to do the same thing with your startup camera?
Yeah, so thanks, Daniel. Definitely, it's protecting the technology is a big problem when you start your company, because competitors usually get around with it. Yeah, definitely you can do it. So what we are doing is a trade secret, but then the pitch sensor company's license agreement only finalized recently, so that will be patented. So it's kind of a double layer. So it's patented, but then keeping as a trade secret. So it's kind of a double protection. But definitely, people can infringe your patent. But then if it is active, Yeah, but I think nobody will do that because it will be a costly decision to infringe somebody's patent if it is filed in a particular country. Yeah, so that's the reason in the startup, the big challenge, as you mentioned, that is protecting your IP is difficult. So usually what companies they do, because we also work with other companies and we filed a joint patent. So when the patent comes, even they change the name. So they will put some, some names that will not come up quickly from the search.
Ah, very clever.
Okay, so
Thank
that's
you.
one trick they use. So that's another trick we learned from people. Another one is if your technology can be infringed, your IP, then we will keep it as a trade secret as well. So that we have another trade secret mark. So that is our technology. Yes. So that's the reason startup also needs some money, because if somebody is infringing, you need some money to pay to your lawyers and to keep your IP safe. So another way is, our IP is safe in the sense because we got investors. So, the investors also are, members in the board, and so they got a vested interest. But the company started by maybe PhD students, so they may have this type of trouble. If they can't find money, they can't keep the IP alive for a long time.
Thank you.
That's a good insight, Ranjith. Thank you. I see that Dragomir actually wanted to ask you a question.
Hey, thanks for the lovely talk, and thanks for the credits for the filters. So I had a practical question, Ranjith. Do you think there is a need for polarization filters in cameras in the applications that you are looking at?
Yeah, definitely, Dragomir. So polarization is one of the important parameters in the light, and polarization imaging is definitely useful when you want to distinguish kind of objects. Yeah, that's another another area. Maybe we can look at it. Definitely there is an application.
Yeah, and one more quick question. So you said you're using 20 megapixel camera. So do you think there is an opportunity to sacrifice some of this spatial resolution for kind of more functionalities? What I mean is like including encoding different information on different parts of the camera. Like one is the hyperspectral, one is the polarization, and so on and so on. Or do you think still this resolution of 20 megapixels is needed?
Yeah, so that is a very, very good point, because we also left, when we made 6 bands, so only 5 bands is having filters, and 1 band was just monochrome. And so because we want to get some particular information that the band was killing that information. Definitely it is possible, so that you can pick up that particular pixel and join with other particular pixel. Definitely we can get it. So we are developing another camera that is called bio-inspired camera, which I did not present today. So that one our interest is actually in the polarization as well.
Thanks, Ranjith. Appreciate it.
Yeah, definitely.
We'll talk more. Very interesting. Yeah.
And especially we are very much interested in the polarization, especially in the thermal wavelengths. You might have seen the DARPA invisible. There is one DARPA call. Actually, they were talking about the polarization.
Interesting. Thank you.
Enhancing the information from the thermal region. Definitely. So same multispectral we can do with the polarization, maybe different polarizations. Yeah, thank you, Dr. Thank you very much.
Ranjith, we are a little bit over time, so maybe one last question, and there was one typed in, and probably I would at least like you to ask half of that question regarding, and this is more about your entrepreneurship activity. And the question that was from Faisal Sheikh is regarding entrepreneurship roles. How do you manage your entrepreneurship endeavors with a full-time academic position? So what is the one big challenge here, and how do you cope with that?
Yes, that's a good question and a practical question. As I mentioned, the big challenge with entrepreneurship when it comes to academics would be the time. So better not to go ahead alone. So better to have as a couple of people join together so that we can share the work. So that's one thing, because we all will be time poor. So another challenge is what we have faced with our company is many people are coming for the product and services, but we don't have people to work for them, because which academic will do the work? So we hire the people, but then they will stay for some time, but then they leave. So then again, we have to hire, and that's also one hassle actually. So the main difficulty of what I find is time. Then how I am managing is, well, I am not managing well. So because we got many people in the company, and so we delegate some work, and then because we got some investment, so we don't spend a lot of time looking into tax return or filing the accounts or such things. We pay money and get it done. Then another problem, that's the reason, as I mentioned, I was involved in 5 startups, only 2 went ahead. Because another 3, I started with the promising technologies with master's students, and when they got the job, they didn't get time to proceed. And if you don't proceed, other companies will come and develop the product, and then the IP will be no more IP. Yeah, but then one good thing is if you look at it, because when I was back in Cambridge, I saw many people when I met entrepreneurs, because I was a member of the Cambridge Entrepreneurs Club. So I met many people, they were struggling to pay their bills, but they got fantastic technology, and they didn't have money. So some people kept the companies and started working, but they never came back. And but then that's the reason I thought, okay, I will start some company maybe when I get a position. So academic position is the best place. Having said that, the other trouble is anyway there for other people. But for us, the good thing is definitely it will increase your track record. You will learn a lot of skills, and the time is worth. Plus, you got a platform to stand on, so because you don't need to pay your bill, and then you also get support from the university. So it's a good venture. You learn actually a lot actually.
So that's fantastic that you got 2 that actually went ahead. It's a pretty good turnout, considering that a lot of startups really don't really go very far in the initial stages. So that's fantastic. So I think we're 3:15. So I think I'm conscious we're really very much over time. But I'm sure that people can still reach out to you. We'll post your presentation, so it will be there for people to listen to again. And on behalf of the chapter, on behalf of Timas as well, we just wanted to thank you again. Thank you once again, Ranjith.
Yeah, thank you very much. And once again, sorry for the technical difficulty due to some reason, which happens sometimes during my lectures as well.
No worries at all. Thanks again, Ranjith. We'll talk soon. Thank you.
Okay, thank you.
Bye-bye.